Hey guys, in this video I'd like to give you an introduction on how to simulate celestial bodies in our universe and compare two different algorithms for this problem. But first and foremost, I want to mention that this tutorial is not suited for beginners since it uses some intermediate to advanced programming concepts, and I will not go over into detail for those trivial problems. So, let's take a look at the simulation first. So as you can see, this is a spiral galaxy simulation where you can see how the bodies exert forces on each other. You can also see those green lines that look like squares. This is the implementation of a so-called quadtree, and this is used in our algorithm to subdivide the area, but I will get to that later. So what do you need to know? As I said before, this is not a beginner video, so you should at least have a basic knowledge of the following topics. You should be familiar with asymptotic complexity and the usage of the big O notation and what it means in regards to runtime and algorithms in general. We will also dive into recursion, so you should have a solid grasp on this, as I will not explain it any further or more than I need to. You should also know about recursive data structures, especially trees, because we will implement a special variety of tree, the quadtree. And also, you also need to know the basics of vector operations and or operations that we use on vectors, such as multiplication, how to calculate the length, and normalizing vectors, and so on. So, let's take a first look at how we calculate the force. So if you don't know already, Newton proved that the force exerted on a body by another body can be described via this equation. G is the gravitational constant here, and m and m2 are the masses of the two bodies, and r is the distance between the two bodies. So if you calculate the limit of this function as r goes to infinity, you can see that this function converges against 0, or converges to 0. So this means that when the distance between two bodies grows, the force exerted on one another decreases. And this fact will prove itself to be useful later on for our algorithms. Okay, now I'd like to show you the first algorithm to calculate the forces, which should be the most intuitive one for most people, and it's called a brute force algorithm. You might know it already from other algorithms. So let's assume all the circles here represent celestial bodies in our universe. If you want to calculate the force exerted on the red body, we would have to calculate the force equation for every other body available and add it all together, and that would be the force exerted on the red body. So you would have to do this for every body, so the total number of calculations would be n multiplied by n minus 1, where n is the number of bodies in the universe. And if you have 100 bodies, for example, you would need almost 10,000 calculations. So that means the runtime of this function grows proportional to n squared, which is not necessarily the most efficient way. And obviously, this is not the most efficient way, so I want to show you a better or improved version where we take advantage of the fact that I mentioned before. So we can use the so-called Barne's algorithm, which runs in nlogn. And as I mentioned before, as the distance grows to infinity, the force exerted on a body decreases, converging to 0. And we can use this fact to approximate forces. That means we calculate the center of masses of bodies that are close together and use this center of mass to calculate the force. Okay, so let's take a detailed look on how it works. So remember those green squares that you saw earlier? Those squares divide the space. We can calculate the center of mass of the bodies inside that space and use this for our calculations. So in simpler terms, we treat those squares as if they were bodies themselves. Okay, so you see those three little blue circles, blue bodies inside the square. We calculate the center of mass of that square and use this to calculate the force exerted on the blue body at the upper left corner. However, we can't just randomly do this, right? There has to be some conditions that needs to be met. So let's take a look at r, the distance to the center of mass, and d, the length of the divided area. So if the ratio r divided by d is smaller than theta is just some constant, we can use this center of mass of that square to calculate the force. But what happens if the condition is not met? Well, then we just go deeper and divide the area again, and at some point we will reach the celestial bodies themselves. So in the worst case, we just take the celestial bodies themselves to calculate the force. So this might happen only if the bodies are too close or to the one that you want to calculate the force for, because the conditions are not met that way. So 0.5 is commonly used for theta. Also, if you set theta to 0, it just means that it calculates the force with every single body, since the conditions are never met, since d divided by r can never be smaller than 0. So in conclusion, we can approximate the force calculation, but it is not 100% accurate. Also, by using the center of masses for calculations, we reduce the total number of calculations immensely if theta is wisely chosen. So that's why this algorithm runs in O nlogn instead of O n squared. Okay, so let's take a look at the fundamental data structure that this algorithm needs, the quadtree. A quadtree is a tree where each node can have up to 4 children. Okay, so each child node represents a square in our space, as you can see here. And the further you go down the tree, the smaller the squares are. And for each and every node, you can calculate the center of mass. So the center of mass of the root, for example, would be the very middle. Okay? I think. I hope I didn't say anything weird now. Anyway, so, okay, our quadtree implementation is clear, or you might now know what the concepts are, but we want to make some detailed implementation now. So if we insert a body in a leaf node that is empty, that body is not the body of the node. Pretty clear, right? So if we insert a body in a leaf node that is not empty, that means that there is a body already inside the node. We split the node into 4 children. So we split this square into 4 squares again, and insert the new and old body into the right quadrants or squares. Okay. If we insert a body B in a node that is not a leaf, we go further down the tree. That means we're not at the end yet. We're not at the leaf yet where we can insert the body. And if you didn't know, leaf means that the node has no children, right? So it means it's like a leaf on a tree. Okay. So now that we know how to calculate or how to build our quadtree, let's take a look on how we calculate the center of mass. So suppose we have 2 bodies with their coordinates x1, y1 and x2, y2. First, you have to combine their masses, and you calculate the x and y position for the center of mass using the formula on the slide. So we can use this to gradually calculate the center of masses for our squares or quadrants when we insert a new body into the quadtree, right? Also, a small side note: the center of masses of leaf nodes are the bodies themselves, which should be very trivial to see. Okay, so finally, I would like to show you some data that was taken by J. Heers. I'm not sure if that's the right pronunciation, but this person's GitHub. And I really suggest you check out their page because they visualized all the steps for the Barne algorithm in a very entertaining manner, and that is also very helpful. So if you want to understand the concepts better that I just told you about, I suggest you take a look at them at that page, since it's really great information, and it's I took this chart from there. So anyway, let's take a look at the naive algorithm, which needs almost 200 milliseconds for calculating 10,000 bodies, right? Whereas the Barne algorithm with a theta of 1 only needs 50 ms. So the difference is quite big. But you also have to account for the fact that if you have a bigger theta, you will also have bigger inaccuracies in your simulation. So the smaller you choose your theta, the more accurate your simulation will be, but the runtime will suffer. So that's it for this video. If you have any suggestions on topics I can cover or anything else, please let me know. I hope I didn't say anything wrong here in this video, and this is only an introduction video. In the next one, we'll start coding, and I will show you the base that I've put up for you guys. And that's it for this video. So thanks for watching, and see you in the next video. Bye bye.